All right, getting into the next problem here. Now, maybe you noticed this is actually that same polynomial that we factored before. All right, where we factored that by the factor by grouping method there. So we take out the negative 25, we get another x plus 5. So then the x squared minus 25 also does a difference of squared, so we have the x plus 5 left over. So one way we could write that in terms of graphing, I know that was sneaky to have the same problem in there twice, but maybe you noticed it, is we could graph this by the roots, just like we talked about in our finding the roots question. So the idea here is I've got a root at positive 5, and I've got a root with multiplicity at negative 5. Now this is a positive cubic, so what do I know about positive cubics? Well, anything positive ends by going up and to the right. And so if you're odd, you will do the opposite of that on your lastmost root on the other side, so we will end by going down and to the left. All right, now what will the multiplicity at negative 5 do? Multiplicity means instead of bouncing through our graph, we will bounce off. Again, this is scaled. It definitely is not only going to go down to negative 3, it'll go way lower. But the idea is that based on the roots and scaling here on the y-axis, maybe this is counting by tens. I don't know. Experiment with it. Look around online and see if you can find what that graph looks like. But you can see that my depiction is probably actually fairly close to what's going on there. Again, bounces off negative 5, passes through positive 5. That's how our multiplicities work with our roots. Even multiplicities will bounce off the x-axis, and odd multiplicities will pass through to the other side. All right? Up next, we've got an exponential function. So we learned about exponentials is that negative 4 is the asymptote line for my graph. I will never be negative 4 because what's happening is negative 4 is either having a giant power of 2 added to it or a very, very small fraction power of 2 because there's a negative exponent. So one thing to do, let's just experiment with that. Let's make a chart just for 2 to the x here, okay? Just for 2 to the x. All right? Just for 2 to the x. Let's figure out what's going on with those exponents. Maybe you didn't quite understand what I was talking about when I was talking about that behavior beforehand. So let's deal with some important values here, like 0, negative 1, negative 2, and 1 and 2. So let's deal with the easy ones. 2 to the first power is 2. 2 squared is 4. 2 to the 0 power, here's where things get interesting, it's 1. 2 to the negative 1 is 1 over 2 to the first. 2 to the negative 2 is 1 over 2 squared. That's a very important exponent rule. It's actually right here. That's why I wrote it on the page. So 2 to the negative 2 is the same as 1 over 2 squared. All right, it's almost like I wrote this page for a reason. All right, now these are before I subtract the 4 from it, so let's see what happens. When I subtract 4 from all these, let's see here. At 0, I'd be at negative 3. At 1, I'd be at negative 2. At 2, I'd be at 0. All right, now at negative 1, I'd be at negative 3.5. Here I'd be at negative 3.25. Here I'd be at negative 3.125, negative 3.16. Or other way around, I'm not saying that quite right. Actually, negative 3.5 is correct, but this would be negative 3.75, because I'm getting rid of the 1/4. This would be negative 3.7/8. Negative 3.15/16. So again, I'm always having a small fraction above negative 4. That's where that asymptote comes from. That's our general shape right there. The next point would be 3, 4, because I would have moved up 8. 2 cubed is 8, so I would have been at 4. So it's not totally correct, but you get the idea of that exponential shape. All right, continuing on, piecewise functions, a few piecewise functions. Piecewise functions are super, super important to understand, but they're very frequently understood. So this section is the domain, and this is what's graphed. All right, so in other words, these two functions will not go as far left and as far right as this picture is. They'll be cut off by where their domains are allowed. So first, I'm just going to draw the whole thing here. This is written kind of out of order. You can reorder that if you want. That's just an mx plus b line. So I got a y-intercept at negative 1. My slope is down 1, right 1, negative 1. Make sure that slope looks negative when you think about what a negative slope should be. All right, so there's my line. But I'm not going to actually draw that in yet because I'm only supposed to be drawing this wherever x is less than 1. And where is x equal to 1? Well, x is equal to 1 right here. Maybe you want to draw that in or think about that as your cutoff point. So I can only be less than 1, not equal to 1. That means this circle right here is going to be replaced by an open circle. And so now my graph actually looks like this. So that's the line, that's what's graphed, but it only goes to the point where I am less than 1. Not 1 exactly, just less than 1. Now, something about these open circles is sometimes we draw them too big. In actuality, what does that open circle look like? It looks like that, or even smaller. You can get as close to 1 as you want. You can be 0.999999999999999. You just can't be 1, so we have an open circle. That's actually why on, if you ever graph a piecewise or look at a piecewise or look at a function that has a hole in a calculator, they're not actually going to draw the open circle because it has that idea that you can be really, really close to it. That open circle has to be very, very small to not get away from the fact that you're actually essentially almost 1. You just can't be 1 perfectly. Anyways, let's draw the other piece. The other piece says I am -5 always. I am the y value -5 always, but I'm not allowed to be that value over here. Actually, I almost drew that perfectly. I can't even really see where I drew, but I'm only allowed to be the value -5 from here on. Oh, and I actually can be, close circle, I can be equal to -5 at 1. So that's my piecewise function. I've got an open circle here. I've got a closed circle here. Where will my graph be graphed, and what am I graphing? So I did that a few more times, and I was trying to be nice and make all these linear. I think one of these extends off the page, but oh well. Got a y-intercept at 2 and a slope of 5. Let's see where I'm graphing that. I'm only graphing that for where I'm less than -2. So less than -2, that's open circle. And that's going to be here. So yeah, that one goes off the page. Sorry about that. Maybe I'll fix that for next year. The next one is just the most basic linear function. Y-intercept at 0, slope of 1. And I can be -2, I can be 3, and all those values in between. So closed circles for those. Up next, I've got a y-intercept at -1 and a slope of 4. So yeah, again, that one's going to start here and go off the page and go like that. So sorry that one looks so crazy, but that would be your answer. You might have thought you were doing something wrong since it was flying off the page, but nope, you were correct. All right, up next, finding inverse of functions. So inverse is where we switch x and y. That's really what you want to think of. When you hear the word inverse, think switch x and y. And now we're going to solve for y. So what I'm going to do that, I'm going to do this kind of quick. I'm going to first add 4, divide by 3, and I've just got y cubed. So now I know my inverse is the cube root of x plus 4 over 3. All of that is inside the cube root. All right, up next, get rid of that little tile. All right, up next, switch x and y. And solve for y. All right, we're going to have x minus 4/7. And then all of that to get y by itself is going to be multiplied by the reciprocal of 3/2. So there we go. Now let's simplify that. It's going to be y equals 2/3 x. I'm just going to distribute it. And when I distribute that other one, it's going to be -8 over 21. So really it's 2/3 x minus 8 over 21. There we go. Up next, ooh, this is where things really get interesting. First, we've got x plus 7. It's 5 to the y. Now I have to get the y out of the exponent. And that is probably the trickiest thing to do. All right? Now, how do we end up getting the y to the exponent? We end up using our logarithms. Now, I'm just going to do the switch here and explain afterwards. But the switch says your base is the bottom of the logarithm. The answer on the other side is inside the logarithm. And the exponent is a solution to the logarithm. So here's a key idea, and it sounds weird in its phrasing, but really try to hear what I'm saying. A logarithm equals the exponent. So this 5 moves to the bottom. And kind of think about it this way. The 5 was on the bottom. It had the exponent, so now the 5's on the bottom. But this is not an exponent of 5. It's just the structure of a logarithm. They're saying 5 is the base. 5 is what was being built upon in this logarithm. X plus 7 is what we were trying to get our exponential to be equal to. And the exponent itself was y. So logs equal exponents. Logs find exponents. So if I want to solve for y, and y isn't an exponent, then the way I'll solve for y is by writing a logarithmic expression. There's another. So doing that opposite now I've got to switch x and y. And so now I've got the opposite structure here where I've got a logarithm equal to an exponent. And I need to rewrite that to get y by itself. Y is trapped inside my logarithm now. So it's before y was trapped in my exponent, I needed a logarithm. Now y is trapped in my logarithm, so I'll need an exponential. Well, the question is, what's the base of this exponential? The base is e. All right, e is the base of ln. So we have e to the x equals y plus 3, which means our inverse function is e to the x minus 3. Understanding how logarithms and exponentials can switch forms and be equivalent, that is super, super important in calculus. And we'll do more logarithm review before we truly dive in to all of calculus. Up next, speaking of this wonderful page right here, all of these exponent rules are super, super important for calculus. You'll see by halfway through quarter one, you'll be using these almost every day. So they're super important to know. And this is your section. And the instructions are kind of weird, but this one just says simplify the expression. Okay, well, let's see what I've got here. I've got some numbers to multiply. This is all multiplication. We can do multiplication in any order. So what I'm going to do is I'm just going to take my 5 and 2 and multiply them. I'm going to take my x's and multiply them. Now let's think about what x cubed and x squared really means. It means I've got x multiplied by x multiplied by x, and I've got x multiplied by x, which means in total I have 5 multiplications of x to itself. And same thing with my y's. I've got a single y, I've got 4 y's multiplying to themselves, so I've got 5 y's multiplying to themselves. All right, an exponent is repeated multiplication of the same thing to itself. So there are 5 x's in total in this expression. There are 5 x's in total in this expression. Up next, here's where things get tricky. It says express with a single fractional exponent. So my first thing I'm going to do is realize that using those rules that I showed you, this is really x to the 3/4 times x to the first. Now, because this is saying we have 5 x's, I was really just adding my exponents when I'm multiplying x's. So same thing here, I'm adding 3/4 to 1, which means I'm adding 3/4 to 4/4, which means I have 7/4. So I've now expressed it with a single fractional exponent. All right. Up next, express with only one x in the numerator in fractional exponents. Okay, this is the same idea. I first got x to the 1/3. I've got x to the first. Now what I've really got there is I've got x to the 1/3 times x to the -1. Or in other words, if multiplication is the addition of exponents, then division is the subtraction of exponents. That's another way to think about that. So I've got 1/3 minus 1, so I've got 1/3 minus 3/3, which means I have x to the -2 thirds, -2/3. So only one x in the numerator. There's no fraction, which means it's in the numerator, and fractional exponents, -2/3. Express with only positive exponents and simplified fractions. Okay, well, I've got 2/16, so that'll simplify to 1/8. Now I've got 4 x's on top and 1 on bottom, so let's think about what that looks like. Well, that means that I have a few x's that are going to cancel, and I'll have x cubed left on top. Same idea, I've got 2 y's on top, 3 on bottom, 2 will cancel, and 1 will be left on the bottom. So I've now expressed this. Don't really need that 1. It can be invisible or implied. I've got only positive exponents and simplified fractions. That's all you had to do. Kind of some wacky wording, but those were the goals for that. All right.